Hey guys, Nick here, and today we're going to take a look at dimensional analysis problems and unit conversions, as well as a little bit about the metric system and how you can deal with density problems, which tend to be a pretty good place where you can find examples of these problems. First off, before we start, as usual, I just want to ask everyone that if you do find these videos helpful, the most important thing you could do would be to drop it in your class group chat. Maybe other people would find it helpful, and it would be a huge help to us to spread the word and get our channel out. So appreciate that. All right, now let's dive right into it. So the concept of units and conversions as a whole is to express things using different sized chunks. So for a familiar example, if you have a distance of 1 meter, you might instead choose to express that same distance in terms of centimeters, a smaller chunk. And within this 1 meter, there are going to be 100 of the little centimeter chunks. Obviously, I can't draw them all in here. So you have a choice of whether you want to describe this length as 1 meter or 100 centimeters, and they're the same thing. Now, to actually mathematically convert between the two, there are some steps you can take. So for a familiar example, before we actually get into the the reliable ways that you'll apply it to your physics problems, we'll just do the familiar way of converting 2 meters to centimeters. Now you know that in each of the 1 meters there are 100 centimeters, so a way you could do it would be to take 2 meters and multiply it by 100 centimeters in each meter. In each meter. And this would give you the answer of 200 centimeters for 2 meters expressed in units of centimeters. Now, something to note here, this is just something you did off of your intuition, and you didn't really worry about canceling out units or anything because it just made sense to you that it's a very simple conversion of 100 centimeters in each meter, and there's just 2 of them. However, as you get to problems with more complicated numbers, or maybe units that you aren't as familiar with, sometimes it isn't even clear which unit is the bigger chunk. It can be very difficult. So what we're going to do is we're going to take the 2 places where meters appears, remember m is short for meters, and we're going to cross them out because one is in a numerator and one is in a denominator. We had centimeters per each meter, and we're left with the unit of centimeter times 2 times 100. So that's a reliable way that you can check that you've done the calculation right, that you haven't accidentally multiplied where you should have divided, or vice versa. Now, in chemistry, this channel will serve, especially this video, will serve physics and chemistry. There's a way to do this to be extra sure that you don't accidentally multiply or divide, and it involves turning these numbers right here into sort of tables. So an example would be if you want to convert 2 meters to centimeters using the typical chemistry way, instead of multiplying, or instead of writing things as fractions like we did here, we would instead write it like this. 2 meters times, and then you're going to do this table to sort of divide up your fractions. So here's one fraction, 2. Here's our other fraction, it's 100 centimeters per, so 100 centimeters is the same thing as 1 meter. And at this point, I want to really point out something to you guys, that all of these conversion factors are just the number 1, right? We started out with 2 meters on the left. That's the quantity we're trying to convert. And every time we are converting it into new units, we're just multiplying by the number 1 expressed in terms of different units. So after that initial number 2 meters, the next box is 100 centimeters over 1 meter. Now those are the same thing, so basically you've just multiplied by 1 to reorganize the distance into new units. So every time you're doing dimensional analyses, you're just doing repeated multiplication by 1. And now you see this this cross in the middle has really clearly divided what thing is being divided versus what thing is in the numerator being multiplied. And now you can really decisively cross out meters because it appears once upstairs and once downstairs. And again, the same thing, you're left over with the units you want, centimeters, which is a good sign. So our answer will be all the numbers in the numerator multiplied together, so 200, and then the leftover unit that we hadn't crossed out, which is centimeters. So this is the rigorous chemistry way of doing unit conversion, which I actually find much more helpful because I'll tell you it's very easy when you get to complicated problems to mix up whether you're multiplying or dividing, or to accidentally cross things out when they shouldn't have been crossed out. Now we're going to do another example where there's multiple units being multiplied together. So in this example, we're going to deal with what is 1 meter squared expressed in centimeters squared. Oops. Now, at first glance, you might say it's going to be 100 because there are 100 centimeters in each meter. But if you were to draw a picture of this, here's 1 meter by 1 meter in an area. And if instead you want to figure out how many little centimeter by centimeter chunks there are in this, you're going to have 100 of those little red chunks on this axis and 100 of the little red chunks on this axis. So in this row right here on the left alone, there are 100 little centimeter squared chunks in this row alone, and there's 100 rows of them. Or I suppose it's 100 columns of them. So really, from our graph, we know the answer is actually 100 times 100. So 100 squared, which is actually 10,000 centimeters squared. So what gives with that? How does the table method tell us how to reliably get 10,000 centimeters squared out as an answer? Now, the thing is, for the table method, we were only able to cross out 1 meter by one factor of meters. If you have something like meters squared, you're going to need to do this conversion factor right here twice. And then each meter in the denominator will cancel out one of the meters in the numerator. So, working on our example here, in the table notation, you have 1 meter squared. So remember, this basically means meter times meter. We're going to need to cancel both of those guys and convert them both into centimeters if we want it to work, properly at least. So we're going to have our 100 centimeter by 1 meter conversion factor here. Remember, this is nothing more than just multiplying by 1 to rephrase our given length in terms of new units. Now again, if you want to do the cancellation, you can't just have this be the end of the story, because this meter can only cancel one of these meter factors. You need 2 of them. So instead, you do this factor twice. 100 centimeter, 1 meter. Now each of these meters can cancel one of the upstairs meters, and your result will have centimeters times centimeters in it. So the answer will be, again, 100 squared, or 10,000 centimeters squared, which is the correct answer. So this is something really important and something that I had a lot of trouble with when I was learning. Be especially on guard for things where you have meters squared or meters cubed. It's very easy to forget that you need to do the multiplication multiple times in order to convert each factor into the new unit. Now, just a side note here, guys, some people, instead of writing this second factor, prefer to just write this first factor squared and leave out the second factor. And that is a-okay. Just remember that that all the numbers inside are squared. So the 100 is squared secretly, the centimeters is squared secretly, and the meter is actually a meters squared, which cancels against the meter squared upstairs. So again, those are 2 equivalent ways, and whichever way you find more comfortable, I would go with that one. All right, now let's get to our first real working example, and it's going to be coming from an in-class problem set I did in a physics class I taught. Let's see if we can figure out how to copy it. Come on. Uh-oh, I'm erasing it by using a white pencil. Aha. Alright, so this is our first game time example. The density of water is 1 gram per centimeters cubed, and we're going to convert that density into kilograms per meter cubed. Now again, we have a few complications here from our earlier examples. The first one being that we have multiple units we need to convert on, the grams and the centimeters. And the second, or I guess the third complication, is that we have centimeters cubed. So remember, when it comes time to convert the centimeters to meters, we're going to need to do it 3 times, 1 for each factor. So let's set out on this. We start out with the number 1 gram per, so since it's in the denominator, I'm going to write it downstairs, per centimeter cubed. And our goal is kilogram per meter cubed. So we're going to try and multiply by fractions that are 1. So for example, 1 kilogram divided by 1,000 grams in order to cancel out grams and work towards getting kilograms upstairs. After that's done, we're going to attack the centimeters and see if we can get meters cubed downstairs instead of centimeters cubed. So like I said, first order business, we hate grams and we want to get it to kilograms. The appropriate conversion factor, we all know that 1 kilogram is the same as 1,000 grams. It takes 1,000 of the little guys to make up the 1 giant kilogram. So I'm going to write out 1,000 grams downstairs and 1 kilogram upstairs. Now again, I wrote it in this flip-flop order because the goal is to cancel the upstairs gram against a lower, or the downstairs gram, leaving us with only kilogram upstairs. So now our final answer is getting worked towards. We have kilograms upstairs instead of just grams. Okay, now we want to attack the centimeters cubed. Now remember, we have 100 centimeters, so 100 of the little guys, in 1 meter. Now you can't stop there because remember, this only cancels 1 of the 3 factors of centimeters that are in the denominator. So we need to do this 3 times. So you can either, again, multiply by this fraction 3 times or just put the cubed there and be really careful to remember that the cubed is hitting everything inside. So I'm going to do it this way because it'll be a little more compact. Alright, we check that we've canceled all the units we want and we're left over with the units that we do want. So we've canceled grams against grams. We have canceled 3 centimeters, so centimeters cubed, against this centimeters cubed. And our leftover units are kilograms upstairs and meter cubed downstairs. So we've got the right units, and now whatever number comes out of all the other numbers will be the number that goes in front. So here we have 1. We have 100 cubed upstairs, and we have 1,000 downstairs. Now, if you do the math, this is 10 to the 6th upstairs, 10 to the 3rd downstairs. So overall, this is 10 to the cubed, or 1,000 kilograms per meter cubed. And that is how now you've successfully converted the density, which was originally in a completely different set of units, into the desired set of units. Now again, this problem had a couple complications compared to the easiest possible stuff, and actually this is pretty close to as difficult as it'll get. It'll just involve more intermediate conversions in between. For instance, you might need to convert grams to pounds and then convert pounds to some other unit. So we'll do an example of that later. But this is a great start, guys. If you've made it so far, you're getting pretty much the core of the concept, and most of the examples won't be too far away from this. Alright, we're going to do another example now. This example is going to be sort of practicing with scientific notation a little bit as well. Just remember, if you are unfamiliar with scientific notation or you want a quick review, we should have a video out preceding this one. If not, it might come out after. So give that a check out if you want any review on scientific notation. All right. So our second example, is giving you a wavelength in microns and asking you to convert to nanometers. So very similar to the problem we just did, there's going to be not just one multiplication, but a couple multiplications to get you to the answer here. But the table method will make it very straightforward, and it'll also provide safety checks to make sure you haven't done something incorrectly. All right, so we start out with a length of 0.66 microns. And the goal is to express this in nanometers. So we want to kill microns with something in the denominator and probably first go to meters because it tells us how many meters a micron is and also how many meters there are in a nanometer. So let's see if we can convert microns to meters first, and then later we'll convert meters to nanometers. So first we have 0.66 microns, and we're going to multiply that by something with a micron in the denominator, and it tells us 1 micron is equal to 1 times 10 to the negative sixth meters upstairs. Again, this is just 1, but written in terms of different units. All right, we're mostly there. We've canceled microns, we're in meters. Now we just want to convert the meters over into nanometers. And it tells us 10 to the negative 9th meters. Again, I'm putting meters downstairs so I can cancel with the meters that's currently upstairs. 10 to the negative 9th meters equals 1 nanometer. Okay, so we've canceled all the units. The only unit left is nanometer. And the numbers that appear in front of it are 0.66. Then we have a 10 to the negative 6th upstairs and a 10 to the negative 9th downstairs. Now, again, if you need a check on scientific notation or a refresher, you can hit up the previous video. But here, if you use our exponent rules, if you have 10 to the negative 9th downstairs, remember that something to the negative exponent really means 1 over that number. So it's 1 over 10 to the negative 9, or 1 over 10 to the 9th in the downstairs. So the 10 to the 9th can be brought upstairs, and the result is 0.66, 10 to the negative 6th. Now the 10 to the positive 9th is upstairs. Again, all we've done is take the 10 to the negative 9th, and at the cost of making the exponent negative, or back to positive from being negative, we've been able to bring it upstairs into 10 to the 9th upstairs. So here we are currently. Now again, remembering exponent rules, if you multiply two numbers with the same base and different exponents, you should add these exponents together. So we get 0.66 times 10 to the 3rd nanometers, which if you want to write this out, remember this is 1,000, which moves this decimal place over 1, 2, 3 places, so 660 nanometers. Oops, M's turn out to be hard to draw. And that's the answer to our example. Now again, this one was more complicated than before. It required two factors to be multiplied on the same unit. We had to work pretty hard to get microns into nanometers. All right, let's do another example. This is going to be converting years to seconds. So example here will be 3 years to seconds. How many seconds are in 3 years? And it turns out there's quite a lot. So we're going to start off with 3 years. Now let's work our way down. We don't have to convert to seconds instantly, sort of like how we didn't convert to nanometers instantly before. So we know that in 1 year there are 365 days. Again, those two numbers are the same thing, so we're just multiplying by 1. In one day, there are 24 hours. In 1 hour, there are 60 minutes. Now we can just check where we are so far. Our years have canceled, days have canceled, hours have canceled. If we were to stop here, whatever number we get would give me how many minutes are in 3 years, but we want seconds, so we're going to keep going. And in each 1 minute, there are 60 seconds. Okay, so our result, the only surviving unit is seconds. And all the numbers here, it's 3 by 365 by 24 by 60 by 60. And if you plug this into a calculator, which I have off to the side of me here, you get that this actually is 9.46 times 10 to the 7th seconds. That's about 100 million seconds in 3 years. It's quite an interesting fact about there's 1 billion seconds in approximately 10 years. Okay, and let's do one more example here, and this one is probably the most important example we'll do today. We're going to convert miles per hour to meters per second. Now, why this is so important is that in physics, it's typical to use meters for distances, and meters per second is your typical unit of speed. However, in America, you often use miles per hour to describe speed more than anything else, maybe feet per second sometimes, but miles per hour. And it's kind of physics teachers' favorite thing to do, to give you the information to the problem in miles per hour, force you to convert it to meters per second, and then plug in those numbers to actually do the problem later. It's just another layer of trickery that gets thrown on. So this is a typical thing that you'll be doing, not plenty, but a fair bit, so it's worth to know how to do. So we're going to start with 20 miles per 1 hour. That's our starting point. And our goal is to convert this miles to meters and get the hours to seconds by the end of it. So first, let's attack the hour because that's easier. We know that in 1 hour, there are 60 minutes. And in 1 minute, there are 60 seconds. Now again, I've kind of flipped the fractions relative to the last problem with the goal of crossing out things in the numerator and the denominator. Now we've ended up with seconds in the denominator, which is good. We don't need to massage it anymore because it's already what we want. Now what we need to do is convert miles into meters. Now this one's pretty complicated because your teacher will probably only tell you this. There's 2.54 centimeters in 1 inch. And you need to therefore go through miles to feet to inches to centimeters to meters, which is a pain, but it's what you have to do often. So let's get to it. All right, we want 1 mile, and we're going to have the intermediate goal of getting to feet and then to inches again, so then we can use this conversion to hop over to centimeters. So in 1 mile, there's 5280 feet. Okay, now we've canceled miles, we're at feet. Let's work feet to inches. In 1 foot, there are 12 inches. Okay, feet have canceled, we're now at inches, we're really close. Now it's time to use this and hop over into centimeters. All right, 1 inch is the same thing as 2.54 centimeters. And now home stretch, we're at centimeters, we want to convert to meters. We have 100 centimeters, so 100 little guys, in 1 meter. So awesome. If we check what units have survived, we have a seconds in the denominator and a meters upstairs. That means whatever number will come out of all these numbers that are being multiplied and divided will be in units of meters per second. So now all there is to collect all the numbers that aren't 1 and multiply/divide them. So the answer is going to be 20 times 5280. Again, these are the upstairs numbers first. times 12 times 2.54. And then in the denominator, we have 2 factors of 60 and 1 factor of 100. And the surviving unit were in meters per second. And if you compute this giant mess right here, it turns out to be approximately 9. So the answer is going to be 9 meters per second is the same thing as 20 miles per hour. Now, this is something really handy to remember. 1 meter per second is about 2 miles per hour. So 1 meter per second is pretty fast compared to a miles per hour. You can also remember this in terms of like world record sprinters. Usain Bolt runs about 10 meters per second, which is about 25 miles per hour. That'll just help you remember which is the bigger unit, which is the smaller unit. That'll be helpful in a way I'll explain later. Now, something I want to comment on is this is something that very often you would Google the conversion if you were doing it on a later problem or a later point in physics where you didn't want to have to do this every time. Now, if you were to Google it, it would tell you something like 1 meters per second equals 2.2 miles per hour, I believe is the accurate conversion. And you can instead just use this shortcut to jump straight from miles per hour to meters per second without doing all these intermediate steps. Basically what this is they've taken all the numbers in here needed to do the conversion. Oops, maybe not this one. They've taken all of these numbers and lumped them together. So instead of having to do every step of this giant circled fraction, they've crunched all the numbers down for you. So as an example of how you do this is you would start out with 20. I started with 20, right? Yes, 20 miles per hour. And you would convert it by doing 2.2 miles per hour is the same thing as 1 meters per second. The miles per hour as a group cancel out. And the result is 20 divided by 2.2, which is almost exactly 9. And leftover units are meters per second. So whether or not you Googled the conversion factor or you were on a test or in a lab and you were forced to do it out by hand, you can get the answer the same way. Obviously, this way is shorter, but it's good to know in principle how you could do it if you really needed. All right, at this point, I want to talk about something that's kind of a fail-safe and an important check to make sure that you have these fractions in the right order, meaning that you haven't flipped them. Because as good as our system is, it's still possible to make mistakes with it. For instance, if you had 1 centimeter and I asked you to convert to inches, it would be really easy, instead of using this one right here, 2.54 1 inch. If you weren't told this explicitly and you just had to remember it, you might very well misremember it as 1 centimeter equals 2.54 inches. And in that case, you would put the fraction in the wrong order and get the wrong answer. Now, the way you can sort of avoid this is by keeping in mind which is the bigger chunk. That's the question you can sort of continually ask yourself just to double check that you're doing it right. So for instance, we know that there are 100 centimeters in 1 meter. 1 meter is the bigger chunk because there are lots of little 1 centimeter guys inside of the 1 meter. So any conversion factor you have should have a lot of centimeters in one of the big guys, one of the 1 meters. Alternatively, sometimes you're going to be given things such as 0.01 meters is the same as 1 centimeter. Now this is also correct, and the way you can tell is one of the little guys, so one of the little 1 centimeter chunks over here, is equal to only a tiny, tiny fraction of the 1 meter big chunk. So either of these fractions is correct, and you can sort of, again, check that in your head by considering which one's the big kahuna, and then which one will have a lot of itself within the big kahuna. At this point, it's also worth referencing something that you'll be using pretty often. Expect to see it on tests. You'll probably be provided with this. So it's very useful to at least know how to use it a little bit. Oops. This is a metric, I don't know, multiplication factor thing. Now, here's exactly what I was talking about. On the right-hand side, it tells you a number, but it doesn't tell it to you very clearly, such as 100 centimeters equals 1 meter. In fact, the number next to centimeter is not 100, but 1/100th. So it's really easy to get confused and multiply by the wrong thing. And this is pretty typical, actually, that the multiplication factor, people don't really care if they give you the number or 1 over the number, even though it's really easy to get the wrong answer if you use it without thinking really carefully about it. So these guys up here, in general, these prefixes are large. 1 unit of these guys is huge compared to down here, these are tiny. So for example, 1 femtometer, there's a ton of those little femtometer guys in something that's higher up on the scale, such as 1 centimeter. Okay, so your conversion factors should look something more like, or actually let's say this is 1 meter and these little green guys are femtometers. Your conversion factors should look either like there's a ton of the little guys, 10 to the 15th femtometers in 1 meter, or 1 femtometer, which is again very tiny, is only a tiny fraction, 10 to the negative 15th, 0.000 blah 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 1 of the 1 meter. So either of these fractions are good, and actually they're the same fraction if you move the exponents upstairs or downstairs. But if you were to flip them over blindly without moving the sign of the exponent, you'd get the wrong answer. So again, it's very useful to check, especially when dealing with these unfamiliar quantities that you don't really know which one's bigger or smaller, to stop and consider which one should be larger based on its prefix. Okay, excellent, guys. I think that is the end. Yeah, that's going to be the end of the section on unit conversion and dimensional analysis. This does tend to be a big learning curve, often because it's one of the first things you do in class. Don't get too hung up on it. You'll get a lot better at it with time goes on, and if you keep doing some examples, you should be on it no problem. All right, next thing we're going to do is move on to density, because very often density and unit conversion go hand in hand. It just provides a lot of places for canceling units to be practiced in an environment that's pretty friendly. It doesn't require too many equations. So let's get to it. We're going to have a short section on density here. Now, density is defined as the mass of an object divided by its volume. Now, there's a mnemonic that you can use for this. Some people use the Greek letter rho. It's kind of like a curly P. Some people use D for density, or lowercase d. It's really kind of ambiguous. I'm going to use rho because D and D are sometimes used for distances, but your professor may do otherwise, so just be aware of that. So again, the definition of density is it's the mass of the object divided by the volume of the object. Oops. And the way you can remember this is a mnemonic that my biology teacher taught me, and it's "Don't Go Breaking My Heart," which is a song lyric. And I guess in this case it's probably more appropriate to use the letter D. on the left for D and don't. So D and then a broken heart, so you put a line through. Here's the letter M, and here's the letter V. So D equals M over V is a way you can remember it if you're ever stuck. Okay, now typically density problems are going to involve you being told two of the three of these quantities. So for instance, you might be told, here's the volume of a ball, and here's the mass of a ball. Calculate its density for me. So let's do an example on this. Okay, let's say we have a ball. Mass is going to be 5 kilograms, and its volume is going to be 2 meters cubed. Okay, and the question is going to be, let's find the density. Now, if we look at our formula, we see we can plug the mass in upstairs. So density, oops, kind of a bad D, is going to be 5 kilograms of mass divided by the 2 meters cubed of volume. 5 divided by 2 is 2.5, and the leftover units are kilograms and meters cubed. So the density of the ball is going to be 2.5 kilograms per meter cubed. Now notice here, I'm still putting units upstairs and downstairs, but I'm not always trying to ruthlessly cancel them like I was in previous problems. In the first half of this video, or maybe I will have cut it into a separate video by then, so in the dimensional analysis video, we were always about killing off units by crossing stuff out and getting the right units. But that was just reorganizing one number into being expressed in different units. This is slightly different. You're actually going to divide masses by volumes and end up with things that are with units that don't cancel. So densities are measured in kilograms per meter cubed. We aren't forced to try and kill the kilograms against the meter cubed, and they can't. One's a mass and one's a volume / length. So, but we're still going to pay a lot of attention to our units and where they are, upstairs or downstairs, because it's kind of like an automatic safety check on your equations. It'll prevent you from accidentally doing things you shouldn't by keeping track of where the units are. Now, in practice, you won't do this all the time, but there are some places, especially when you're stuck or a problem's really difficult, where it's really good to put the units back in and keep track of them. So we're going to keep doing it for now. Let's do another example where we're given two different properties of the ball, and again, we're asked to find the third from the equation. So let's say this time we're given the volume and density of the ball, and we're asked to find its mass. So the volume, we're going to say, is 0.3 meters cubed. Density will be 7 meters cubed. And we're going to ask, what is its mass? Now again, our equation is the broken heart, M over V. We know what density is, so we can plug in 7 meters cubed over there. And we know the volume is 0.3 meters cubed. And mass is left alone upstairs. Oops, sorry, did I say density is 7 meters cubed? I meant to say kilogram per meter cubed. Sorry. Okay, so we can multiply the 0.3 meters cubed over onto the left side. Basically, we're multiplying both sides of the equation by 0.3 meters cubed. So we have mass is 7 kilograms per meter cubed times 0.3 meters cubed. Now again, we're going to keep track of the units, see what cancels. Some things will, some things won't. The meters cubed cancel against each other because one is downstairs and one's upstairs. And we are left with just kilograms, which is good because we're asking about a mass. So the result is 7 times 0.3, which is 2.1 kilograms is the mass of the ball. Excellent. All right, let's do a third example where we're given the final pair. Now again, this is because density is used as really the first numerical thing you do in physics, so it's really good to get all the examples you can out of it. All right, let's say this time we're given the density. So the ball density is going to be 10 kilograms per meter cubed. And mass is going to be 50 kilograms. What's the volume is going to be the question. Now, here I plugged in numbers before rearranging. This time I'm going to take the opposite approach. I'm going to rearrange the equation first and then plug in numbers. That's how most people do it. It tends to be a little cleaner. So we have density is mass over volume, and we're hunting V. So it makes sense if we can get V by itself on one side of the equation. That way we just plug the numbers into the other side of the equation, and then it tells us what V is. So what I'm going to do is first I'm going to multiply V, or both sides of the equation, by V. Okay, now I'm at M equals D times V. Okay, and again, our whole goal is to get V by itself. Very helpful to keep that in mind. So we want to get stuff away from V. So it makes sense to divide both sides of the equation by D to get rid of the D that's attached to the V. So our equation is now V equals M over D. And now it's time for us to plug in numbers. So for our situation, we have a mass of 50 kilograms and a density of 10 kilograms per meter cubed. Okay, let's check what units die versus survive here. Now, we have kilograms upstairs and kilograms downstairs, so those cancel immediately. Now, we have meters cubed in the downstairs of the downstairs. Now, if you remember, if you ever have 1 over something, it's the same thing as just the something being upstairs. So we have 1 over meters cubed, so that's the same as just meters cubed in the numerator. Perfect. So meters cubed survived, and that's a volume just like we liked. So we've checked that we've done everything right. And the number out front is 50 over 10, or 5 meters cubed is the volume of the ball. Excellent. Okay, now we're going to do a challenge example that wraps up everything we've covered in this video, or again, if I have split the video, it's going to cover unit conversion. Scientific notation is probably already going to be its own video, and density all in one. So this is a great example coming from one of my professors. Ooh, come on. All right. This question is actually something pretty relevant if you are pre-med or biology or anything medical track, how much blood you can take from a person and how much it'll weigh. This is a problem relating to that. So it actually is pretty good real-world application here. So we're going to be told the density of blood, and a person on average will donate about a pint of blood or something on the order of a pint of blood during a blood donation. And you're going to wonder how much mass of blood, I guess that's blood cells plus the like the fluid it's in, how much mass of blood does a person donate? Now, unfortunately, the density is given to us in kilograms and meters cubed, and the volume is given to us in pints. So we're not able to immediately multiply things out because the units won't cancel properly. We'll get weird numbers. So first, we kind of have to convert the pint into meters cubed of volume. Then we can finally multiply by density to get mass of the blood donated in kilograms. And then at the very end, it wants us to express that instead of kilograms of mass donated in grams. So at the very end, we'll do that conversion. All right, so let's start. We donate 1 pint of blood. And again, our goal is first we want to convert this to how much meters cubed of volume of blood we've donated. So it tells us that 1 pint is the same thing as 2 quarts. Oh, sorry, other way around. 2 pints. So the pints are the little guys, are the same as 1 quart, the big guy. Okay, pints have canceled. We're at quarts now. It tells us 1 quart equals 0.947 liters. Okay, now we're at liters. Again, our goal is to get to meters cubed. It tells us 1 liter is 1,000 centimeters cubed. Now, by the way, this is not 1,000 centimeters cubed. This is 1,000 centimeters cubed. Okay, this is not that. Okay. All right, now we want to convert centimeters cubed into meters cubed. Now remember, this 3 is going to cause some problems if we aren't careful about it. So we have 100 centimeters per 1 meter, and we need to do that 3 times. That way the 3 centimeters will cancel off with each other. Just as a reminder, this 100 is cubed. Okay, perfect. Now we're at meters cubed of volume donated. If you compute this number out, you get 4.7 times 10 to the negative 4th meters cubed. And again, this number represents, it's good to keep track of that, the volume of blood donated. Okay, that's a partial answer. We're more than halfway through the problem. Now we want to use the density to convert this volume into a mass of blood. So remember, the governing formula is density is mass over volume. We want to know the mass, so it makes sense to get everything on m's side away. So we multiply by v on both sides to get it away. So we have mass is density times volume. Now we have a density of 1.06 times 10 to the 3rd kilograms per meters cubed told to us. And we are donating a volume of blood that's 4.7 times 10 to the negative 4th meters cubed. Okay, let's do the unit not the unit conversions. Let's cancel whatever units we have. So we have meters cubed upstairs, and we have a meters cubed appearing in the denominator. So those cancel, and the surviving unit is kilograms. And the surviving numbers are 1.06 times 10 cubed, and then, I'm going to run out of room, 4.7 e negative 4. By the way, this e notation, e negative 4, is the same thing as times 10 to the negative 4th. Okay, and if you plug this into a calculator, what you end up getting is 0.502 kilograms of blood. So this is the mass of blood donated. And all that's left is to convert these kilograms to grams. Now by this time, you guys are experts in that. You have 0.502 kilograms times, well, in 1 kilogram, which is a big guy, there's 1,000 of the little guys, grams. So the answer is going to be 502 grams of blood donated. That is the mass of the blood that you donated. And in doing this problem, even if you didn't get it completely right, because I'll admit, I forgot the 10 cubed in, let's see, in this step right here. I forgot to cube the 100 because I didn't draw this little arrow, which is why I'm drawing it now. So even if you didn't get it completely right, if you understood the general process that you're going through, great job on that. This really incorporates a ton of different skills, so excellent work. All right, that's going to wrap up the video for this time, guys. Next time, we're going to take a look at vectors and trigonometry, so stay tuned for that. That's another really difficult subject that examples can really help you navigate through. And once more, if you did like the video, if you want to do us a huge favor, like the video and particularly drop it in your class group chats to spread the word to as many people as possible. All right, till next time, guys.